Welcome back. Now you may be watching this video because you were interested in electrostatics. Well, I'm here to show you four problems in electrostatics and how to solve them. First, let's get to the first question. Three 2 microfarad capacitors in parallel are connected to in series to two 3 microfarad capacitors in parallel, all within a circuit connected to a 12-volt battery. We are tasked to find the equivalent capacitance of the circuit and the voltages and charges of every capacitor. Now, how are we going to solve this? The first thing we're going to do is to actually draw the circuit here. So, 12-volt battery. Let's just put a big battery here, And then, three 2 microfarad capacitors. So, there are three capacitors in parallel with each other. So, like that. All of these are 2 microfarads. Yeah, all those are just 2 microfarads, so don't worry about it. Then they are in series to a set of microfarads. This time there's 2 of them, and they are 3 microfarads each. And they're all connected to this 12-volt circuit, and there we go. That is the circuit that we are going to be talking about. Now, what we want is the equivalent capacitance of the circuit. How do we find that? Well, first we have to simplify the circuit into smaller chunks. So, for instance, these three 2 microfarad capacitors, we can add them together. From this table here, capacitors in parallel are sum. So you just add capacitance in parallel. So these are capacitance in parallel. We can add them up. 2 plus 2 plus 2 makes 6 microfarads. So the equivalent capacitance of that is going to be 6 microfarads. So let's draw a simpler circuit with replacing this as one capacitor. This is the equivalent capacitance of this entire thing. So this entire thing, this is the equivalent capacitance. So keep that in mind. So this is 6 microfarads as we discussed right there. 6. How about this one? Well, these are 2 3 microfarad capacitors. So they're also 6 farad. 3 plus 3 is equal to 6. So I don't need to tell you that. So there you go. That is the circuit. And now, since they are in series, the equivalent capacitance of 2 capacitors in series is the harmonic sum. Again, a reminder: the harmonic sum is this. C is the capacitance here, so the harmonic sum is something like that. In a calculator, if you want to find the harmonic sum of, let's say, 6 microfarads here, first you have to press the number 6, then to the power negative 1, right? Then you do that for every other capacitor. So if you have like 4 microfarads, you could write 4 to negative 1. But for here, we just have to input 6, alright? Then you will get an answer. The answer you get would be something like 0.333 dot 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 dot. And then you press the negative 1 again, the power negative 1, you will get the capacitance, which is going to be 3. 3 microfarads is the equivalent capacitance. So we have 12 volts here, and we can combine all the capacitors. We know that this would be 3 microfarads. That is the equivalent capacitance. So the equivalent capacitance is equals to 3 microfarads. Alright. So the second part of the question is to find the voltages and charges of every capacitor. So how are we going to do that? Well, first of all, we need to find the charge of the entire thing. We know the equivalent capacitance. We have the total voltage. We can find the we can find the charge using the formula capacitance equals charge over voltage. So capacitance, denoted as Cp here, but you can denote it as C, equals Q over V. Q is the charge and V is the voltage. Alright, so we need the charge, so we can say charge. We get Q equals CV or CPV, whatever you want. Let's just put CP here, so no, let's just not put it there. Let's just put CV. There we go. Now we have the capacitance, 3 microfarads. We have the voltage, 12 volts. So we can multiply them together. We get 36 microcoulombs. You have to pay attention to the units, because here the unit is microfarad, and then we multiply it by volts. We get microcoulombs. But if it's like microfarads and then nanovolts, it's a different unit altogether. So you have to be careful about that. But since there's only one micro here, we can just put micro on the resulting unit, and it's just microcoulombs. There we go. So the total charge is going to be 36 microcoulombs, while the voltage is 12 volts and the equivalent capacitance is 3 microfarads. Let's make a table. So let's label every capacitor here as A, B, C, D, and E. Alright, let's put a table here. A, B, C, D, E. Let's put here C, capacitance, V, voltage, and Q, or small q, for charge. Now, we need to list down what we already know. So, we know that the capacitance is 2 microfarads here, 2 microfarads here, and 2 microfarads here. And that is all in series with 3 microfarads here, 3 microfarads here. So these three are in parallel, these three are in parallel, and the overall capacitance is 3 microfarads. This is the total or equivalent capacitance. How can we find the voltage? How can we find the charge? We know the total charge is going to be 36 microcoulombs. So first we can find the charge. We know that from the table, charges in parallel are the sum. So you have to add the charges up in order to get the total charge. And charges in series are equal. So if capacitors are in series, the charges of those capacitors are equal. So the group ABC is, as we can see here, is in series with DE. Again, this is the equivalent of ABC. This is the equivalent of DE. So they are in a series with each other, and charges in series are equal. So the total charge of A, B, and C should be 36 microcoulombs. And it is the same with D and E, 36 microcoulombs, since the charges in series are equal. But since A, B, and C are in parallel with each other, the A plus B plus C, the charges there, must equal to 36. So what is the charge? So what is the charge in each? First, we need to find the total capacitance. So the total capacitance is just adding this, since capacitance in parallel is the sum. So just add it. So the total is 6 microfarads here. Let me put it. 6 microfarads. Okay. So the formula again is Q equals CV, but we can arrange that so we can get the volts. That will be Q over C, charge over capacitance. The charge we have is 36 microcoulombs, and the capacitance we have is 6 microfarads. This will give us 6 volts. Right? The micro and the micro here cancel each other out, leaving us with volts. And volts in parallel are equal. As it says right here, voltage in parallel are equal. So we can put 6 volts all around here. Right? They said also that voltage and series are the sum. So, look at here. So all this have 6 volt, uh, 6 volt voltage running through it. So that means the equivalent voltage is 6 volts, since voltage in parallel are equal. And then voltage in series are the sum. So this has a total of 12 volts. According to Kirchhoff's law, this should have the amount of voltage drops here should have same here. It's for resistors, but it also applies here. So this has 6 volts. This has, the total is 12 volts. 12 minus 6 is equals to 6. This also has 6 volts. And voltages in parallel are equal, so this both have 6 volts. Nice. Alright, now that we have Q, now that we have C, and now that we have V, the only missing is Q. Again, the formula for charge is Q equals CV. So we can multiply this and that together in order to get the charge. So capacitance times voltage. 2 microfarads times 6 volts is 12 microcoulombs. And it's the same for all of these three. And if you add them together, 12 plus 12 plus 12 is 36 microcoulombs, which is exactly the total. So that's good. 3 microfarads times 6 volts is also, 18 microcoulombs. And this is also 18 microcoulombs. And if you add them together, you get 36 microcoulombs. And that is the answer. The total voltage here is given to us, it's 12 volts. And that is the answer. That entire table right there. Alright. Alright. Question number 2. Hold on. And there we go. Question number 2. Let me just move it here. There we go. Question number 2. A cylindrical resistor 10 meters long has a diameter of 3 centimeters. The resistivity of the material is 1.2 times 10 to the 3 ohm meters. What is the resistance of the object, given that the formula is R is equals to rho L over A? So we're given the three other, we need to have the three other aspects to find resistance. Rho, which is the resistivity, the length of the material, and the cross-sectional area. A cylindrical resistor should look like this, which is what every resistor looks like anyway. The cross-sectional area is the area of this parallel is plate right here. The problem says we have a diameter of 3 centimeters. That is the diameter. We need to find the area. Okay, 3 centimeters in terms of meters is 0.03 meters. That is the diameter. The radius should be 0.015 meters. Alright. So the area of a circle, I hope you still remember this from elementary, pi r squared. And we have r here, so pi times 0.015 meters and then squared. Input that in your calculator. You get something along the lines of 7 times 10, hold on, 7.067 times 10 to the negative 4 square meters. And that is going to be the area, the cross-sectional area that we're going to be using. So rho is 1.2 times 10 to the 3. Multiply that by L, which is 10 meters. Divide by this. I forgot the unit here. Sorry. The unit, you shouldn't forget the unit, is ohm meters. Over 7.07 times 10 to the negative 4 meters squared. And using your calculators, you can calculate what the sum is. So let's do that. 1.2 times 10 to the 3 times 10 divided by 7.07 times 10 to the negative 4. We get the answer of 1.697 times 10. Hold on. I got the figures now. This is actually 16.97 mega ohms, or 16.97 times 10 to the 6, or 1.697 times 10 to the 7 ohms. Yeah, so it's going to be mega ohms, so it's a very resistive resistor right here. Must be made of rubber or something, but I just. Question number 3 is about magnetic force. So hold on. Alright. A 12-meter wire in the below configuration has a current of 3 amperes and a magnetic field of 4 Tesla. What is the direction and magnitude of the magnetic force? Let's assume that the magnetic field is perpendicular. The formula is F equals beta IL sine theta. Theta in this case is 90 degrees since it is perpendicular, and sine 90 degrees is just equal to 1. So we can safely ignore that. And let's just proceed to the actual formula. Force equals beta IL. F force, again, this is F is force. Beta is the magnetic field. I is the current. And L is the length of the wire. Yeah, there you go. So what is the direction and magnitude of the magnetic force? Now, in order to find the direction of the magnetic force, which is the first thing we should be doing, we have to use the right hand rule. Let me draw a hand here. For example, this. Pardon my drawing. Alright. So imagine this is your hand. The thumb represents the direction of the current. The hands represent the direction of the field, the magnetic field, and the palm represents the force, the magnetic force. So let's do this. The current, in my view, is this direction, so it's going that way. The field is going X, which is into the page. So if you're looking at a piece of paper, something like here, the X denotes that it's going into the page. Okay? If it's a dot, it means it's going out of the page, into me. But since it's X, it's going into the page, like that. So in that way, and my thumb current should be going that way. The magnetic force, meanwhile, should be going up, since my palm is pointing up. If I was to high five someone, they should high five from the top. So, like that. So, we can safely say that the force, the direction of force, should be going up. But what is the force? Well, the formula is F equals beta IL, sine theta, but sine theta is also already 1, so you can forget that. Beta is the magnetic field, so magnetic field is 4 Tesla given here. The current is 3 amperes given here. And the length is 12 meters given here. Multiply that together, we get 144, and the unit for force is Newton. Reminder, this is the MKS system, which is the meter, kilogram, and the second system. There's another system in CGS, which is centimeter, gram, second, and the imperial system and whatnot. But for the most of the scientific world today, we use MKS. So don't have to worry about that. You do have to worry if you're using, for example, a stat coulomb or stamp, but usually we just use MKS units. And time for the last question. Right. Hold on. Here. Two parallel wires 200 millimeters apart have opposite directions of current but have the same current of 5 amperes. What is the magnetic field vector at point 50 at a point 50 centimeters from the right as shown in the diagram? Assume free space. Now, what is it talking here? So, these have 5 amperes of current, but they're going in this specific directions, up here and down here. And they're 200 millimeters apart, and if we convert that into meters, we get 0.2 meters. And this is 50 centimeters apart. If we convert that into meters, we get 0.5 meters. So obviously, the diagram is not to scale, so but we don't have to worry about that. This is the point. So we need to find the magnetic field vector. So magnitude and direction. First, let's find the direction because that's important. How do you find the direction here? Well, if you're carrying a pen, which you usually are because you're answering this exam, uh, you have to curl your hand like this. Now, what are the guidelines for that? So, for example, let me draw like a bigger arrow here. For example, here. Here is the direction of current, and here is the point of a vector. What you have to do is to rest your thumb like this, where it is near the current. Don't rest your hand like on the other side. Rest your hand on the same side as the force. So on my side, this is it's like that. And watch where your thumb is. So my thumb right now is pointing inwards into the page, which is denoted by X. So the direction for the up here is X, like that, because it's going that way. All right. Now for the down, let me go down. For the down, and then we have a point here. Similar thing, but you have to flip it around and then look at where your finger is now, right here. So it's a bit tricky to find it. Let me just illustrate it using this. I see. Alright. So, if you put your thumb again on the same side, my fingers are pointing towards me or out of the page, which is denoted by a dot. So, in here is denoted by a dot. Alright? Let me do it again. So for the one going up, ball pen going up, and then the thumb is going near the point charge, which is here. For example, here. It may be reverse on how you view it, but my point charge is going here. So the thumb should be right here. Then I will curl my fingers on the ball pen, and then I will watch where where my fingers go. So my fingers go that way, there, into the page, denoted by X, right? Same thing for the upside down. The thumb has to be close to the point charge. Again, my fingers are pointing towards me or out of the page, which is denoted by a dot. All right. So after you find the directions, we can now find the magnitudes. So let me erase all of this. All right. All right. So first one. 5 amperes, 0.2 meters here, but there's 0.5 meters here. So from the current of 5 amperes, there is 0.7 meters total here. Again, because there's 0.2 here and then 0.5 here, so adding them together makes 0.7. So, what is the magnetic field? Magnetic field is this is the formula. Beta is mu 0 of times I over 2 pi r. R is the distance, I is the current, and mu is the permeability of free space. Free space. Usually, air can be considered free space. It has a small enough coefficient of free space, but this is free space, and we're assuming free space anyway in the question here, so that's good. Now, you just plug everything in. Again, there's 1.26 times 10 to the negative 6 Newton per ampere squared multiplied by the current, which is 5 amperes, over 2 pi times the r, the distance, 0.7 meters. So we just calculate that using the trusty calculator. Make sure it's board certified, otherwise you're going to struggle finding one of these. This is not board certified, by the way, this is illegal. But anyway, the magnetic field, my calculator says, is 1.43 times 10 to the negative 6 Tesla, and in other units, 1.43 microtesla. Alright, that's the first one. And the direction, of course, don't forget, is the X, denoted by X or into the page. As for the down, current of 5 amperes, and the distance from here to here is 0.5 meters. Let's apply the formula again. Alright, and this is 1.26 times 10 to the negative 6 Newton per ampere squared times 5 amperes, which is the current, over 2 pi times 0.5. And the answer is 2.01 times 10 to the negative 6 microtesla, or no, not microtesla, just Tesla here. Sorry. Tesla, or 2.01 times no, just I keep making this mistake. Microtesla point going into your face or out of the page. Now, how do you find the total magnetic field? Again, before we start anything, let's label this. This is from the left arrow, so this is beta left, and this is beta right. This is the arrow from the right. So, how do we find the overall magnetic field? What we're going to do is to assign positive to something. So, for this instance, let's assign X as the positive. So, this is positive. This should be negative since it is going out of the page. So, let's assign that as negative and see what happens. So, beta equals beta L plus beta right. Our beta L is 1.43 microtesla, and since it is into the page, it is positive. It is positive. Then, 2.01 microtesla, since it is out of the page, it is now negative. 2.01 microtesla. The answer is negative 0.58 microtesla. It's negative, therefore it is into the page. Since since into the page is positive, this means that out of the page is negative. So this means that the magnetic field total is 0.58 microtesla into out of the page. And that is your answer. Thanks for watching. I hope you pass the exam tomorrow. Bye.